dear learners. In today's lecture, we will try to understand various important aspects about Earth's ionosphere. In this series of 8 to 10 lectures, we will understand Earth's ionosphere, its chemistry, and other dynamical aspects related to Earth's ionosphere, even the electrodynamical aspects, etc. Right. So, Earth is one of those planets which has an intrinsic magnetic field and a very active ionosphere. So, what is ionosphere? Ionosphere is basically a region of the Earth's upper atmosphere in which there are sufficient number of electrons and ions. So, we are referring to it as an ionosphere, where you are referring to the presence of or indicating the presence of ions. Okay. But more importantly, in this course of solar terrestrial physics, we will try to understand how the sun influences or affects various things in the Earth's atmosphere, and we will try to extrapolate this understanding into other terrestrial planets, their atmospheres as well. So, for starters, we will try to understand the Earth's ionosphere, other aspects, very important aspects about the Earth's ionosphere. Right. So, if you look at this figure shows the neutral atmosphere, which is shown on the left. So, neutral atmosphere is basically a characterization of the Earth's atmosphere depending on how the temperature varies with respect to height. So, temperature does not decrease in a linear way away from the surface. It initially decreases and then increases and then decreases and then increases. So, marking the turning points of this temperature versus height curve, we define these 4 layers of which are called as troposphere, stratosphere, mesosphere and thermosphere. This is very basic, all of you must be knowing it. But if you have followed other courses of NPTEL related to atmospheric and space sciences, you may have also been familiar with ionosphere. But since we are building a continuous flow of ionosphere, various things related to ionosphere, we will try to start from the basics of the ionosphere itself. Right. So, ionosphere on the other hand is characterized not based on the temperature or not based on the thermodynamical parameters. Rather, we use the electrodynamical parameters related to the Earth's atmosphere. So, at some point of time, it was realized that Earth's upper altitudes, Earth's upper atmosphere has a significant population of electrons and ions. So, it so happens that the total number of electrons are approximately equal to the total number of ions in this region. And then this region of the Earth's atmosphere was being referred has been referred as ionosphere. Okay. So, ionosphere basically contains these 3 layers, D region, which is the bottommost region of the Earth's ionosphere, E region, which is just sitting above the D region, and then the composite F region, which is made up of F1, 2 distinct layers, which are F1 and F2. Right. Now, for all practical purposes, how do you define ionosphere? Ionosphere is that region of the Earth's atmosphere where electrons and ions are present in sufficiently large numbers to be able to influence radio wave communication. Right. Now, you are talking something entirely different from what the neutral atmosphere or the aspects related to neutral atmosphere that we are familiar with. So, we are talking about radio wave communication, we are talking about electrons and ions. This state of matter which exists in these altitudes is referred to as plasma. So, ionosphere is a region where there is a lot of plasma which is present, right? And now, what we are going to understand in this series of lectures is that why we have different layers. Why don't we call it as a continuum? Because since there is, if you talk about the neutral atmosphere, the characterization of neutral atmosphere into troposphere, stratosphere, mesosphere and thermosphere is only valid when you are talking about the variation of temperature with respect to height. If you don't bring in temperature into that picture, if you only talk about the way the neutral densities are changing with respect to height, you would not have all these regions. neutral density or the number of molecules per unit volume will keep changing from the surface in an exponential way. It will only decrease in an exponential way. The same variation translates very well into the pressure or density, right? These two parameters are one and the same, right? There we don't discuss about layers. If you ask me how do you characterize based on the neutral density variation, then probably I would say I can characterize something where there are atoms and molecules which are uniformly mixed. I will call it as a homosphere and heterosphere. Where what I'm referring to is if atoms and molecules are well mixed, then if you consider any unit volume of the atmosphere, you will realize that this volume contains, let's say, uh, nitrogen, oxygen, and other trace species in the same ratio that we know that the entire atmosphere is representative of, right? But when you maybe if you go on increasing the altitude, you will find a region where the species are not uniformly distributed. Rather, they are distributed as per their individual scale heights, right? So that is where you are introducing the aspect of turbulence or turbopause, or you are referring to the non-uniform mixing of the atmosphere, whatever it is, right? Now, in essence, if you talk about the variation of temperature with respect to height, you get all these layers. So how do you define these layers? These layers are simply those altitudes, or uh, the are simply the yeah, make an edit here. These layers are basically those regions within which the temperature trend will be a constant. Either it is increasing or decreasing, as simple as that. But when you translate this into the ionosphere, it's not very simple in all these layers in D, E, F, right? So, in essence, in ionosphere or the discussions related to ionosphere, we will try to understand how these layers form, what are the photochemical aspects related to this, the formation of these layers, what are the theories, mathematical theories or theoretical explanations which can explain how these layers form, the structure of these layers, etc. And then we will, since it is a plasma, the medium, the entire medium is a plasma, we will try to understand some electrodynamical aspects related to this ionosphere. Then we will try to understand uh, phenomena which are called as equatorial ionization anomaly, etc., the fountain effect, etc., for the which are very well needed for a comprehensive understanding of the ionosphere. Then we will try to extrapolate all these basics and try to understand what is the conductivity of ionosphere, on what parameters does this conductivity depend, and how many different types of conductivity exists in the ionosphere, etc. And that is pretty much about the ionosphere that we are going to learn in this course, right? So the ionosphere, the atmosphere above the 70 kilometers altitude is partially ionized. So you see, partially ionized, it's not completely ionized. So there are, in addition to electrons and ions, we also have neutral species which are not ionized. Okay, so ionosphere is a region where electrons and ions are present in addition to neutral species in sufficiently large numbers to be able to influence the radio wave communications. Okay, so this region is formed by the ultraviolet radiation. Where is the ultraviolet radiation coming from? Ultraviolet radiation is of this solar origin. So ultraviolet radiation creates this or populates this ionosphere. So this region of partially ionized gas extend upwards to high altitudes where it merges with the magnetosphere. So what is magnetosphere? Magnetosphere is a bubble around the planet Earth, within which the magnetic influence or the magnetic strength of the Earth is dominant or can be observed. Okay, so magnetosphere is a bubble. It is a bubble which has been formed by the solar wind. So solar wind, when it interacts with this magnetosphere, there is only a limit up to which the solar wind can enter into the proximity of the Earth. This limit is decided by the strength of the Earth's magnetic field. So Earth, for all practical purposes, can be considered as a simple dipole magnetic field. Okay. So it extends into the space. It has a 1 by r cube dependence. So in all the directions, it will be there. And as you go away from this dipole, the strength of the magnetic field will decrease. So coming back, so magnetosphere is simply a region surrounding the Earth where the Earth's magnetic field is prominent. Okay. So the ionosphere is not something uh, which exists for all the planets. Of course, it exists with different strengths around different planets. Okay, so the ionosphere was discovered in early 1900s in connection with long distance radio wave communication. So when you talk about radio wave communications, generally, if you don't expect long distance radio wave communication is always achieved between two antennas, one transmitter and another receiver. So depending on the distance by which these two antennas are separated, yeah, the communication will become effective. So if they are far too apart, if they are within the curvature of the Earth, you can achieve communication. But if they are beyond the curvature of the Earth, then the radio wave communication, direct radio wave communication or line of sight communication is not possible. But then in very early 1900s, radio wave communication was achieved far beyond the line of sight distance, and people realized that this uh, uh, radio wave communication over such a long distances was only possible if only there was a mirror or a reflecting surface in the sky somewhere, so that the radio waves are falling on that reflecting surface and are reflected towards the larger distances where the signal is received, right? So scientists then postulated, or rather proved, that long distance radio wave communication was only possible due to the reflection of an ionized region in the atmosphere. So when you have a plasma medium, it will have its own refractive index, and refractive index is a crucial parameter which will decide whether, depending on the angle of incidence, of course, whether an electromagnetic wave will be transmitted, reflected, or attenuated. All these possibilities, right? So then, fundamentally, scientists realized that long distance radio wave communication was only possible due to the reflection of an ionized region in the sky or in the atmosphere, right? So to sum it up, we have what is ionosphere. We know what is ionosphere. Why ionosphere is relevant? Because it helps in radio wave communication, right? How and why are the things that we will understand in this class, right? So if you look at the neutral classification of Earth's atmosphere, you have all these regions: troposphere, stratosphere. We already talked about, right? So these are the turning points where the temperature trend is getting reversed, and as long as it is same, within this it is increasing, within this it is decreasing, and within this is decreasing, and again it is increasing, right? So that's why we have troposphere, mesosphere, stratosphere, troposphere, mesosphere, stratosphere, and thermosphere. Okay. This is the neutral characteristic, right? And when you look at the variation of various species in the Earth's atmosphere, so most dominant ones are the nitrogen and oxygen. You see the oxygen density at, let's say, 800 kilometers. At larger altitudes, even much below that, the atomic oxygen density seems to be larger than the density of molecular oxygen or molecular nitrogen. This is because of the incoming solar radiation, which dissociates molecule into atoms, right? But in essence, what this figure tells you is the variation of density in an atmosphere with constant temperature, let us say 750 Kelvin. So all these densities are decreasing with respect to height. Right. Now, this is the neutral characteristics, neutral densities which are available. Now, you put this in combination with the incoming solar radiation, because solar radiation is fundamentally is the only driver which regulates or which drives all the physical chemical processes in the Earth's atmosphere. So you have to always think about how the Earth's atmosphere interacts with the solar radiation or solar energy input. if you want to broaden the horizon and discuss more aspects related to the Earth's atmosphere, you should talk about solar energy. Energy received in terms of electromagnetic radiation, particles, etc., etc. Okay, plasma, right? But when you talk about how the Earth's atmosphere interacts with the electromagnetic radiation, we should know the electromagnetic radiation that we receive from the Earth is a composite wave, is a composite light source which has wavelengths spanning from X-rays all up to infrared radiation. What are these radiation? These radiations are all uh, of different wavelengths but the same speed. Their wavelengths differ. To compensate the difference in wavelength, the frequency changes in inverse way to the wavelength, which means larger wavelengths will have smaller frequencies and vice versa. And larger the frequency, more is the amount of energy that that particular radiation possesses. Right now, so this radiation can be assumed to, for a practical purpose, can be assumed to be from 0.1, let us say, nanometer, almost up to 10 to the power of 6 nanometers. This you are going to call as XUV or UV, and this you are going to call as infrared. So, which means the solar radiation is bundled into this window of wavelengths, right? Now, more importantly, each of these wavelengths can have different effect on the Earth's atmosphere. When you talk about effect, how the radiation interacts with each of these atmospheric species is of very importance to us. Okay. Now, let us look at these radiation one by one. We call X radiation. Okay. Let's say 0.1 to 10 nanometers is what we call as X radiation. X-rays, we are familiar with X-rays. X-rays are very energetic, very low wavelength, very high frequency. Okay. So X-rays, what are X-rays capable of? When X-rays interact with an atom or with a molecule, they can ionize the atoms, which means if you have an atom X and this photon in the wavelength of X-rays interacts with it, it will create, or it will ionize, it will remove the outermost electron, creating a positive ion, and of course, an electron which has been removed, right? So X-rays can dissociate molecules, which means it can dissociate molecule, let's say N2, into N and N, etc. Okay, it can ionize, it can knock off the electrons, outermost electrons, almost any gas. So we are talking about almost any gas, which means we are in the case of Earth's atmosphere, we have only nitrogen and oxygen, which are the most important, or which constitute 98% or 99% of the Earth's atmosphere. So we don't have anything else. Let's say we don't have any other gas. We don't have H2SO4. We don't have vapors of H2SO4. I mean to say, we don't have any other gas which can be, which is as prominent as these two species. So they alone make 99% of the Earth's atmosphere, right? So they can dissociate or break apart molecules when they are absorbed. Okay, so they can ionize molecules, atoms. They can ionize molecules as well. So they can directly produce N2 into N2 plus, and absorbed by almost all gases. So all the gases, for example, carbon dioxide, nitrogen, oxygen, argon, all these gases can absorb X-rays. Absorption means when this radiation is absorbed, it is not like it indicates that either an electron is removed or electron is being sent in a very in excited state, etc. Then comes the ultraviolet radiation. Ultraviolet radiation is also energetic. We can say ultraviolet radiation within EUV, XUV, everything. We can put it together, put as 10 to 100 nanometers. Okay, 10 to 100 nanometers, or if you are going for far ultraviolet radiation, you can go almost up to 350 nanometers. So ultraviolet radiation don't pack the amount of energy that much amount of energy that the X-rays pack in them. ultraviolet radiation can dissociate some molecules, can dissociate, okay, and can also ionize some atoms and molecules, some atoms. The ultraviolet radiation is very well absorbed by ozone and water vapor. We know ozone is there, not so much, but in the stratosphere. So what happens is, ozone molecule, due to the presence of the uh, molecular energy bands which are suitable, which match very well with the wavelength of the ultraviolet radiation, can absorb the UV radiation. As a result, we don't receive that much amount of ultraviolet radiation on the surface. Water vapor, which is also abundantly present in the Earth's atmosphere, also is a good absorber for ultraviolet, right? So looking back, we have X-rays which can pretty much ionize anything, dissociate all the molecules. Then we have ultraviolet, which can dissociate some molecule and can also contribute towards ionization. Then you have visible. Visible is like 350 to 700 nanometers, which don't pack a lot of energy, which is required for ionization or dissociation. So as a result, they won't get absorbed by any gas. So in physics, we clearly know, we know very well that the excitation can only happen if the incoming radiation energy matches with the exact energy gap or energy difference between two energy levels. So it so happens that the visible radiation is never enough for this transition of the most important species, which are oxygen, nitrogen, argon, let's say H2O, O3, right? So as a result, the electromagnetic radiations passes is the entire medium or the entire atmosphere is simply transparent for the visible radiation or for the visible radiation, and some photons are scattered. This is a different thing. Infrared radiation, of course, it is even larger in wavelength in comparison to visible, ultraviolet, and X-rays. So they carry very less amount of energy, okay, and the frequency is very very small. Okay, so infrared radiation cannot ionize anything, but it is a good absorber of greenhouse gases. What are the greenhouse gases? CO2. Most important greenhouse gas is CO2. CO2 has the ability to retain the the infrared radiation. You see this figure, infrared photons are absorbed by molecules, causing them to vibrate and rotate. So the vibrational excited states or the rotational excited states in a molecule, like even N2 or CO2, match with the infrared wavelengths. So what happens? So infrared radiation is absorbed by these trace species or greenhouse gases. So when you talk about the short wave radiation, which is coming from the Earth, and the long wave radiation, which is going from the Earth, you can realize that the long wave radiation is trapped by the carbon dioxide, which is present in the Earth's atmosphere. So if you increase the carbon dioxide which is present, it will trap more amount of infrared radiation which is going out. Infrared radiation is nothing but the heat. As a result of this trapping, the average temperature on the planet will increase. So more amount of CO2 in the Earth's atmosphere, more amount of infrared radiation is trapped, and as a result, the global temperatures will increase. Right. So we are talking about ionosphere in these two spectral wavelengths. We are talking about transparent atmosphere in the visible, and infrared radiation can be used, or infrared radiation is the key parameter, key component which contributes or which is needed for understanding the uh, climate change. Right. Why are we talking about this? We want to understand the ionosphere, how it forms, why it forms, when it forms, how does it vary, etc., etc. So we realize that ionosphere exists only because of the interaction of solar radiation with the Earth's atmosphere. How does it interact? This is how it interacts. Right. Now, you take the incoming solar radiation, incoming sunlight. Okay. Incoming sunlight contains all the wavelengths, which is almost from 0.1 nanometers to 10 to the power of 6 nanometers. This figure shows 0 to 3 micrometers. Okay. And E lambda is the amount of energy per unit time, per unit surface area within d lambda of 1 micrometer. Within one, so amount of energy absorbed within, for every 1 lambda of spectral window, 1 micrometer, 1 micrometer, this figure is generated. So, what you see is spectral intensity of sunlight near the Earth space. So, when it is at the top of the atmosphere, okay, you measure the intensity of light versus wavelength, intensity, the amount of energy that is there at every lambda you measure at the top of the atmosphere. This is how you get. Okay, but when you measure it Earth's surface after the radiation travels the entire atmosphere, this is what you get. So, what is the difference between these two, or what is the difference that you observe is that the bottom one, the second one, its intensity is less, the energy that is packing is less. Where did the energy go? All the this portion of energy, all this, where did it go? It is what has been absorbed. So, the difference between these two lines is simply the amount of energy that has been absorbed. Who is absorbing it? So, this part is absorbed by ozone. This is water vapor, molecular oxygen, water vapor, all this water vapor, carbon dioxide, the water vapor, and right. So, you see the micrometer. So, this is 1.5 10 to the power of minus 6 meters. Okay. So, you can see that all the infrared radiation is very well absorbed by the greenhouse gases. Okay. Right. Now, if you further extend this, this is the attenuation. So, incoming radiation is by the sun at approximately 6000 Kelvin or 5780 Kelvin as shown in this figure, and 255 Kelvin is the average temperature of the Earth. So, black body curves for these two will look something like this. So, this peak will fall in the visible region, and this peak will fall in the infrared radiation. So, the sun can be considered as a black body with lambda max in the visible region, and Earth is a black body at 255 Kelvin at a lambda max of how much? Infrared radiation. This is the basic difference. Why this difference exists? Because the temperature of the black body. Okay. So, this is the absorption curve where all the missing lines or the missing energy wavelengths are talking about a particular species which has absorbed them. Okay. So, this is at 11 kilometers and this is at the ground level. Okay. Now, you know 99.9% of the Earth's atmosphere, or to a broader estimate 99% of the Earth's atmosphere exists within the first 30, 40 or 50 kilometers, right. So, as a result you see this absorption curve. Okay. So, we will continue this discussion learning about more important aspects about the Earth's ionosphere.